Welcome to my classroom. Today we're going to explore planet Earth through the power of aerial photography. It is my goal to assist you in identifying specific man-made structures and natural objects in an aerial photograph. I will also demonstrate the use of dimensional analysis to determine the size of an object in reality from an aerial photograph, and vice versa. So let's get started. So what is aerial photography? Well, aerial photography is the process of taking images using an aircraft or flying object. Today, these images are taken daily, used to monitor changes over large portions of Earth's surface. They might be used to track the growth of a local wetland or monitor the presence of pollutants. They can be used by city planners to analyze traffic patterns to design new paths that mitigate congestion or allow you to more easily grab that cup of coffee. They can also be used to assess impact of some of the world's most devastating storms. This video shows the devastation left by Hurricane Isis in 2020 along the North Carolina coastline. Regardless of the purpose, aerial photographs provide crucial information about the ever-changing surface of Earth. But to see Earth's surface, we need to get high up in the sky. And there are many ways to achieve this. One way might be a hot air balloon. These massive balloons use the basic principle of temperature to climb high in the sky, always supporting a creative design and providing exquisite views. However, they are not the most practical mode of transportation. You might be more familiar with a more recent invention, the drone, or more officially, the unmanned aerial vehicle. While they were originally designed for military operations and have become an essential component of a 21st century military, they are becoming more popular throughout various industries. They can easily monitor Earth's surface, providing crucial information to those who need it. They have become rather inexpensive, allowing the everyday consumer, like ourselves, to get in on the action. But what about before such advances in technology? Before the drone or even the airplane? What would they use? It might surprise you or be a bit nonsensical, but they actually used nature's own aircraft, birds. What better way to take an aerial photograph than through the eyes of those who have been surveying Earth's surface for millennia? In 1907, a few years after the Wright brothers first took flight, a German apothecary submitted a patent for the pigeon camera. These pigeons were fitted with a small camera equipped with a timer. They were originally devised to track the flight of pigeons, but showed wartime promise. However, they were beat by the development of the airplane. Even those elite pigeons weren't as reliable, though, as our metal birds of today. But they did capture some of the very first pictures of Earth from above, a view we have become accustomed to in our everyday lives. Today, aerial photographs are so deeply ingrained into our daily lives that we rarely even think about them as we scope out new places to visit or plan new trips along routes of interest. For this activity, though, we're going to take a more analytical approach and see what we can learn from an aerial photograph. So let's put on our surveyor hat and see what we can learn about this unknown location. I can probably guess the first thing you notice in this photo. It takes up a large portion of the image and grabs your attention with its straight, angled roads. This is Mueller Airport, located north of downtown Austin, Texas. You might have quickly recognized the airport from other airports you've seen from above or ones you've experienced firsthand. You might have even seen those little planes dotting the tarmac. This airport exhibits the main characteristics of man-made objects. They usually consist of straight lines with these very precise angles, demonstrating the beauty of human engineering. They usually appear very light in color, reflecting light instead of absorbing it. Do you see any other man-made objects in the photograph? One that appears densely throughout this image are homes. If you look at this particular region, you can see straight lines with evenly divided plots of land. This is a portion of a larger housing community, with many scattered throughout the photo. If you look at a particular house, you will again see the straight lines and sharp angles of human design, typically appearing light in color. Do you see any natural objects? They tend to be much more darker. For example, look at this area of the image. It is much darker and almost has a grainy look to it. This is a portion of dense vegetation. I can't necessarily tell if it's composed of trees or bushes, but I can definitely see the irregularities of leaves, giving it that nice grainy look. Vegetation, such as trees, bushes, and grasses, typically appear darker because they absorb light. However, if you have one of those nice tailored grass lawns, they're typically a bit lighter than an unkempt grassy area. Just below this area, you can make out an unusual shape. What do you think this is? That's right, it's part of a road. But is it a small back road or a highway? Yeah, this is characteristic of a highway. This is an exit from one of the main highways in North Austin, Texas. What about this area? Do you think it is a natural or a man-made object? Maybe it's just a really windy back road. Not quite, right? You might have guessed that because of the light portions coming through. But I'll give you a hint. Those light areas are created from exposed areas of a riverbed. That's right, it's some type of stream. Streams always run from high elevation to low elevation, so you could check yourself with a quick topographic overlay, but they are also very windy. They flow the path of least resistance, lacking those straight and crisp lines of human engineering. Let's try a challenge. What do you think this portion of land is used for? Pause the video and look closely. Can you figure it out? If we look closely, it appears relatively light, but not as light as the runway of the airport. So it's probably one of those grassy areas. If we look closer, we also see that it's broken into these irregular oval-shaped areas. Figured it out yet? It's a golf course. Great work! Now you have the tools to qualitatively analyze an aerial photograph. However, as we've demonstrated in the examples, aerial photographs can be used to monitor changes through time. This photograph was taken in 1995. Let's see how the area changes through time. Pick a particular location on the image to focus on. Now let's see how it changes. Where'd the airport go? If you were from Austin, you probably were already questioning an airport in North Austin because it no longer exists. The Mueller Airport provided service to Austin area up until 1999, when it was closed with the opening of the Austin-Bergstrom Airport. This provides a large area for development close to the city center. As you can see, most of the area has already been bought, sold, and reinvented. Looking at the area as a whole, you can see much more housing, a more dense urban area when compared to the photo from 1999. You might even live there and have no idea it used to be an airport. If you want to check out the history of your location, watch my video on the historical records of Google Earth. You'll be able to explore the history of many locations around the globe. We've covered our first mission. You now have the necessary skills to analyze and use an aerial photograph qualitatively. But what about quantitatively? What if we wanted to know how long the runway was, or the areas of a particular housing development? Well, let's find out. We can also use aerial photographs to calculate distances and areas. I will start by showing you how to calculate the length of this bridge in meters from the provided aerial photograph. Let's say I measure the length of this bridge to be 12 centimeters on the aerial photograph. Can I use that information to determine its size in reality? Of course I can. I merely need to perform a dimensional analysis calculation. Now I know, dimensional analysis, complicated term. Not really. It's just a fancy term that just means that I'm converting from one unit to another unit. In this case, we want to be able to convert from centimeters on the photo to centimeters in reality. But how? Well, we first need a crucial conversion. At the bottom corner of this photo, you'll see a value of 1 to 12,000. This is the scale of the photo. You can think of it in a few different ways. You can think of it as how many times the photo has been scaled. In this case, the photo has been scaled 12,000 times down from reality. You can also think of it as the link between the photo and reality. For example, a centimeter in the photo is equal to 12,000 centimeters in reality. That means that if this bridge was 1 centimeter long in the photo, it would be 12,000 centimeters in reality. It turns out that the scale provides a linear link between any linear unit of measure. It could be centimeters, it could be feet, it could be meters, it could be miles, it could even be kilometers. But not any nonlinear unit, like a unit of area, such as centimeters squared or meters squared. For each calculation, I will use subscripts to help you keep track of what I'm talking about. I will use a subscript P to indicate a measurement on the photo, and I will use a subscript R to indicate a measurement in reality. For example, this scale would say 1 centimeter in the photo is 12,000 centimeters in reality. I'm going to solve this problem two ways. The first I refer to as the stepwise method, which breaks down the problem into individual steps. For the bridge, we not only want to calculate how long the bridge is in reality, but how many meters long the bridge is. To do this, we need to start with the measurement on the photo, or centimeters in the photograph. We are then going to convert that to meters in the photograph, and finally meters in reality. This is a two-step process, indicated by the two arrows in the diagram. For our first step, we begin with the measurement from the photograph, 12 centimeters. You can see that I use the P to indicate photograph. We want to convert this to meters on the photograph. Since we are staying in the photograph, we don't need the scale just yet. We are going to use what we call a conversion factor to move from one unit to the next. A conversion factor is just a relationship between the two units that is always true. It is set up as a fraction, with the unit that we are interested or want divided by the unit that we have. For this conversion, the unit that we want is meters in the photo, and the unit that we have is centimeters in the photo. Now we need a true relationship between the two units of measurements. The one I always use is that 1 meter is equal to 100 centimeters. However, you can use any relationship between the two units that is true. You could use 0.01 meters, you could use that 2 meters is 200 centimeters, but for our cases, I'm going to stick with 1 meter is equal to 100 centimeters. Now we just need to do the math. You can use a calculator if you need to, or you can move the decimal. If we think through the problem, right, 12 times 1 is 12, and 12 divided by 100 is 0.12 meters, because we move the decimal 2 places to the left. One step done. We've converted it to meters in the photo, as you can see indicated by the subscript. For the last step, we need to convert the meters in the photo to meters in reality. We do this in the same fashion. We want to multiply by a conversion factor, again, what we want, over what we have. In this case, we want meters in reality, and we have meters in the photo. Do we have a link between these two units? Yes. This is where we need the scale of the photo. It tells us that 12,000 meters in reality is 1 meter in the photo. Now we just need to do the math again to get that the length of the bridge is 1,440 meters in reality. Great work! You just did your very first dimensional analysis problem. On many occasions, you have to convert between units multiple times, and instead of doing an individual calculation for each step, some people use what I call the train track method. We are still going to follow the same path of converting from centimeters in the photo to meters in the photo to meters in reality. However, we're going to set up a series of conversion factors, or those ratios of what we want over what we have. Our first is we're going to start with the centimeters in the photo. Our first conversion factor is between meters in the photo and centimeters in the photo. We add the same conversion factor we used in the previous path as a track this time. The next track is the conversion factor from meters in the photo to meters in reality. Now we just do the math. We multiply all the numbers on top, or 12 times 1 times 12,000, to get 144,000. We do the same on the bottom to get 100. We then divide 144,000 divided by 100 to get 1,440, the same answer that we got in the first problem. A common mistake that students make when constructing their train tracks is the units. You should always check to make sure you are left with the unit you want in the end. To do this, we cancel or mark out units that appear on top and bottom. Like, for example, centimeters in the photo and centimeters in the photo is on the top and the bottom. We also see that meters in the photo is on the top and the bottom. That only leaves meters in reality on the top, which is the unit we want. Now you have two different methods for solving unidimensional problems. Pause the video and try it yourself. Calculate how long the bridge would be in reality if it measured 10.5 centimeters in the photo. Thanks for trying. You should have gotten 1,260 meters. But what about the area of something? Maybe we wanted to estimate the area of this courtyard. Let's say we estimate the size of the courtyard on the aerial photograph to be 3.4 centimeters by 1.7 centimeters. Now we can use the same two methods we learned before to solve for the area in meters squared. We will start with the stepwise method. We are going to approach the problem as two unidimensional problems, i.e. we're going to do one for each side of the courtyard. We will start with one side in centimeters in the photo, convert it to meters in the photo, and then meters in reality. We will then follow the same path for the other side, centimeters in the photo, meters in the photo, and meters in the reality. Once we have both sides in meters in reality, we will use this to calculate the area. Given that the area of a rectangle is length times width, we will multiply both sides to determine the area in meters squared in reality. Let's start with one side. We start with 3.4 centimeters in the photo and convert to meters in the photo using the same method as before. We multiply by a conversion factor of what we want over what we have. We want meters in the photo, and we have centimeters in the photo. Again, we need a relationship. 1 meter is 100 centimeters. Now we do the math again, move the decimal 2 places, and get 0.034 meters in the photo. We then need to convert to reality using the same method that we did before. We need to multiply by what we want over what we have. In this case, what we want is meters in reality. We have meters in the photo. The relationship is the scale factor, 14,000 to 1. We do the math, and we get 476 meters in reality. Now we have one side. Next, we need to perform the same calculation for the other side. Now, with both sides, we can calculate the area of the lot in meters squared. By multiplying both sides, we get an area of 113,288 meters squared in reality. Great work! But that's not the most friendly number. Units are chosen based on their convenience, making it easier to convey their meaning. That's why we say we want a dozen eggs instead of 12, or a large instead of 16 ounces. A convenience unit for area is called the hectare. 1 hectare is equal to 10,000 meters squared. If we convert this value to hectares using the skills we've learned, we can see that it is a much easier value to convey. It's approximately 11 hectares. We can also solve this problem using the train track method. We can create a train track for each side and then use the converted size to determine the area. This demonstrates how to use train tracks to calculate the length of one side as an example. If you like the train track method, try the entire calculation to see if you can calculate the same area that we calculated in the stepwise method. We've solved the problems using different methods, but use the same pathway. However, there are many pathways to solve the problem, and we welcome them all. It is up to you on the path that you choose to take. Let me show you one of these alternative pathways using the train track method. We're going to focus on the top pathway. For this pathway, we're calculating the area first by multiplying the length by the width in the beginning. We can then set up our train track, but there's one catch. The previous tracks we created only used linear units. These units are not linear, they're area units. This means that the relationship must be scaled accordingly. Let's start with our area of centimeters squared in the photograph. Our next track should be what we want, or meters squared, over what we have, centimeters squared. Again, we need a relationship that is true. We can't use that 1 meter is 100 centimeters because that is not the right unit. We must square the value since the unit is also squared. Therefore, on top, it should be 1 squared, or 1, and on the bottom, it would be 100 squared, or 10,000. That's an important change that many students make as a mistake. So pay close attention to any time a unit is squared. If the unit we want and the unit we have is squared, we must square the linear relationship. We would do the same for the scale. To see if you are following me, try to calculate the area in hectares to see if you can get the same answer from the stepwise calculation. Pause the video and try it yourself. What would be the area in hectares of the lawn if it measured 4.5 centimeters by 6.2 centimeters in the photo? You should have calculated it to be 550 hectares. We have one more topic, and it has to do with the area I just reported. You might have wondered, why did I round the area to 550 hectares? The reason? Significant figures. All measured values must be reported to the correct number of significant figures, the digits that contribute to the degree of accuracy. They make each of us honest by providing details about the accuracy of the device we use to make the measurement. For example, let's take a look at the posit example. I could have reported the area of the lawn as any of these values, 547, 546.8, 546.84, 546.840. However, each choice has a different number of significant figures. The higher the number of significant figures, the more accurate the measurement. I've told you the number of significant figures in each value, but let's cover how I got them. I have provided you with 3 different measurements, each with a different number of significant figures for us to count. The first rule for significant figures is that all non-zero numbers are significant. I've highlighted each of them in orange. The real trick in determining the number of significant figures are the rules for zeros. Any zero between 2 non-zero digits are significant. I've highlighted them in gray. And all leading zeros are significant, also highlighted in gray. The last example I've given you is a bit tricky. If there is no decimal, then there are no significant zeros. But if a decimal is added, then they become significant. You can think of a decimal as a way to signify that they are significant. Using these rules, we can see that the first measurement has 4 significant figures, the second also has 3, and the last one has 4. While these rules might seem bizarre, they begin to take shape if we look at a few example measurements. In this example, a measuring device, I need to determine the value of each hash mark before I can actually use it. To do this, I count each space between 0 and 1. 10 total spaces. That means that each hash mark represents 0.1. I'm going to mark the middle one so we don't forget. Now let's use our measuring device to measure the width of this green strip of paper. We can see that the edge of the paper falls between the 0.5 hash mark and the 0.6 hash mark. We could just estimate that it's closer to the 0.5 hash mark, but that is not using our measuring device to its fullest potential. We can actually estimate to the hundredths place based on where it falls between the 0.5 and 0.6 hash marks. It appears to me from this image that it falls right in the middle, so I would record the answer to be 0.55. Always remember that we estimate 1 past the hash mark. It would be ridiculous for me to estimate that it's 0.555 because I can't visualize that from this device. Therefore, this measurement would have how many significant figures? 2. Let's change our scale of the measuring device by 10 to see how this affects the number of significant figures. And that means that also the thickness of our paper is going to change compared to our measuring device. We know there are still 10 spaces between 0 and 10, so each hash mark must then be equal to 1. So let's mark the middle as 5 so we don't forget. The thickness of the paper has not changed, but now our measuring device is less accurate because the edge of the paper now falls between 0 and 1 instead of the 0.5 and 0.6 hash marks. Therefore, the best we could estimate from this device is 0.5. That is one less significant figure than the previous device we used. As you can see, the number of significant figures tells us how accurately the measurements were taken. Try it yourself. Can you match each measurement to the correct number of significant figures? We've covered how to determine significant figures, but what about using measurements in calculations? We have to ensure that we don't inflate the accuracy. Therefore, we follow a set of rules based on the operations to minimize this. If the calculation only requires multiplication or division, we report the answer to the least number of significant figures of the original measurements. In this example, 1.7 has 2 significant figures, and 3.41 has 3. Therefore, the least number of significant figures is 2, so our answer should be reported to 2 significant figures. Note that we only took into account the measured values. Conversion factors are considered to have infinitely many significant figures and never, ever determine the number of significant figures in your answer. If the calculation only requires addition or subtraction, we report the answer to the least number of decimal places. Given that 9 centimeters has none, the answer will also have none. Lastly, if you have a mixed operation problem, then you report the answer to the least number of significant figures among both rules. For example, the addition portion of this problem would suggest that the answer have 1 decimal place, while the multiplication would suggest 2 significant figures. Therefore, I could either report the answer as 16.6 following the addition, or 17 following the multiplication. Given that 17 has the least number of significant figures, we would report our answer as 17. Okay, we've covered all the rules, but why does it matter? Well, let's take 3 different balances. These are the devices that you use in your science classroom to measure mass. Let's say each of them has a different accuracy. The first measures to, let's say, the hundredths place, the second to the thousandths, and the last to the 10,000th place. This means that as we move from left to right, we are increasing in significant figures. This is also directly related to the cost of the device. As you can see, as we progress from left to right, the price of the balance increases 5-fold. Significant figures does matter. It also matters in terms of gemstones if I'm looking at clarity of diamonds. It might also be more related to when you're purchasing your next TV, when you're focusing on resolution. While money does matter, it is more important to remember that the value is placed on the highly accurate measurements, or in this case, the highest resolution you can get in a television, the highest clarity you can get in a diamond. Just like you want to have the best image on your TV, scientists value the most accurate measurement. Therefore, it is important to be honest about your accuracy when reporting measurements. Today, we've learned how to analyze an aerial photograph qualitative and quantitatively. We reviewed how to perform dimensional analysis calculations and report answers to the correct number of significant figures. Again, thank you for joining my classroom. Stay inspired and explore more videos.